Hello everyone, Robert McEwen here. Welcome to our first video on calculus as part of our Mathematics for Economics course. I'm going to explain to you what calculus is. I'm going to explain to you how we use calculus in economics and business, and I'll give you some examples of real-world applications. And then we're going to get into understanding how to compute a thing called derivatives using limits. Remember, before you learned about limits, limits was a way of looking at a function as its independent variable got very close to a value like, say, maybe 0, but wasn't equal to 0. And so we're going to use this concept of limits to come up with our first calculus results. What is differential calculus? Well, simply put, differential calculus is about finding the slopes of curves and other complex functions. So you already know how to find the slope of a line. The slope of the line is equal to the rise over run, which is the change in y divided by the change in x. And we've already done a fair bit of work in this course working with the slopes of lines. Remember that another way to interpret the slope and a real-world application is to think of the slope as the rate of change of a function. So if we change x by 1 unit, by how much does y change? We call that the rate of change. The rate of change is the slope. They are one and the same. Today, we're going to spend our time learning how to calculate something called the instantaneous rate of change. This is also called the derivative of a function. What do we mean by instantaneous? I already told you what the rate of change is. Rate of change is, say, we change x by 1 unit, how much does y change? The instantaneous rate of change says if we change x by some tiny infinitesimal amount, basically the change in x is almost equal to 0, by how much will y change? We call that the instantaneous rate of change, making that change in x as small as possible. Now, why is calculus useful in business and economics? Well, you can think about the previous slide, understanding the rate of change of more complex functions, curving functions, exponential functions. That could be useful. In what practical ways is it useful? Well, optimization, something we'll learn later in this course. Firms want to maximize profits. Firms might also want to minimize cost, given profit at a certain level. And it turns out that these slopes are extremely helpful for optimization problems. They make optimization problems much easier to solve. In economics, we are very interested in marginal analysis. We want to know what happens at the margin. The margin in economics often is related to the word change. So if we have a small change in taxes, how is that going to affect business investment decisions? Or if there is a small change in taxes, how is that going to affect government revenue? We're interested in modeling. So we're going to look, when you're in second year macroeconomics, or if you're taking macroeconomics with me, you'll learn about the Solow growth model. It's a time series model, so it looks at how economies evolve over time. And calculus is extremely useful for understanding that evolution over time. Finally, you can think of elasticity. If you've taken an introductory microeconomics course, you would have learned about elasticity. One way to define elasticity is the responsiveness of a change in demand to a change in price. How responsive? Is it inelastic? Is it elastic? You might remember something called the midpoint technique. Well, with calculus, we don't need to use that midpoint technique because we can use the instantaneous rate of change that I mentioned on the previous slide. So this is an idea of why calculus is useful and why it's particularly why it's useful in economics and business. It has lots of really useful applications. And when I say that, what do I mean? I mean, it takes complicated problems like optimization and makes it a lot easier to understand. As I mentioned earlier, measuring the slope of a straight line is straightforward. It's the rise over the run. But now if we compare a line to a curving function like the one you see before you, it's quite different. For example, what would a line look like if I drew just a straight line? You can appreciate that the rate of change is constant all across that line. So if I look at the change, say here, it's going to be the same anywhere along that line. If I try and do the same drawing technique, I'm going to get a different slope at different points along the line. They might be the same at certain points, but they're going to be different at other points as well. And that makes our formula, our equation over here, that means it's not going to work. Now, Isaac Newton and Gottfried Leibniz, they, working independently in the 17th century, they essentially invented calculus in order to calculate the slope of a curve, or the rate of change at a curve at any point. And they did this by taking advantage of the fact that we know how to find the slope of a straight line. And so the first key insight they had is this idea of a tangent line, or applying a tangent line to the problem. A tangent line is a line that touches a curve at a specific point, and at that point where it touches the curve, it has the same slope as the curve. That's important. It's going to have the same slope as the curve. So please allow me to demonstrate. In front of you, we have a curve. It's a quadratic function. And we're being asked to draw a tangent line with a point of tangency at the coordinates 2, 12. I'm going to go ahead here and draw a tangent line. And it's always a little hard to see on these graphs, but the tangent line only touches f of x at one point, and we might say that the point is right here at coordinates 2, 12, x equals 2, y equals 12. And so if we know the slope of the tangent line at this point, then we're going to know what the slope of f of x is at the point 2, 12, at coordinates 2, 12. And this is the goal that we're going to have going forward from here. We're going to try to find a tangent line at the point of interest where we would like to know the slope of the curving function. Here's a quick summary of what I did on the previous two slides. We drew a tangent line. Tangent line just touches a curve at a single point, and at that point where it touches the curve and the line have the same slope, the same rate of change. Okay, that's great. There's this tangent line that we believe exists. If we know the slope of the tangent line, we can find the slope of the curve. But how are we going to find the slope of the tangent line? Well, we're going to use another concept called a secant line. A secant line is a line that crosses a function twice or more, but we're going to focus on the points where it crosses a function twice.